In a previous video, we looked at these three infinite series. The first one had terms that alternated between positive and negative, and the individual things we're adding up stayed the same size, 1, negative 1, 1, negative 1. And in the last two, the terms that we were adding up got smaller, so we had 1, negative 1/4, plus 1/9, and so on, and then 1, negative 1/2, plus 1/3. And we saw that the one where the terms stayed the same size diverged, and the ones where the terms got smaller converged. And so based on that observation, we might make a hypothesis. And in order to write this down precisely, I'm going to use the following notation. I'm going to assume that Bn refers to the positive ones where you've taken the absolute value, and that An are the alternating terms. All right? And so our hypothesis it might be that if we have an alternating series and the terms are getting smaller, so if Bn goes to 0, then the sum of An converges. Now, want to avoid confusion here. That looks a lot like the nth term test. But remember, we said that for the nth term test, if the terms go to 0, we cannot conclude anything. So this is a little bit different. This is not for any series. It's for an alternating series. But if we have an alternating series where the terms go to 0, then, at least based on our examples, it seems that the sum is going to converge. And we will actually show that this is the case later on. All right, so that's our first observation, that it seems like what you need to get convergence for an alternating series is just have the terms get smaller. Okay? All right, second observation. And for the second observation, I want us to look actually at the numerical solution, and we'll focus in on that last one. All right, so let me bring up Desmos here. All right, so we're looking at the series negative 1 to the 1 plus n over n, which the terms go 1, negative 1/2, 1/3, negative 1/4, and so on. And what I want you to notice is that as I add more terms, our first partial sum was bigger than the limiting value. The next one is too small. The next one is too big, then too small, too big, too small, too big, too small, too big, too small. They alternate back and forth. And so each time we add a new term, we're basically overshooting the true value. And what that suggests is that if you take two consecutive terms for an alternating series, that the true sum must lie somewhere in between. Again, this is assuming that it actually converges. All right, so let me write that down. So hypothesis. If the sum of An converges to S, then S is in between Sn and Sn plus 1. Okay? If you take any consecutive terms, the true sum has got to lie somewhere in between there. All right? So that's our second hypothesis. Again, we're not proving these statements. We're just trying to make some observations based on these examples. All right? One more hypothesis. And again, we'll go back to our numerical solution for that. All right, so let me scroll back a few terms. All right, so let's say that I've got, I've added up 5 terms. So I've got a partial sum with 5 terms. And notice that the fifth red dot seems to be above the limiting value. Suppose that I wanted to say how far off is S5 from S? You know, is using the fifth partial sum a good estimate for the sum where I include all the terms? Well, notice that if I know that my next term is going to be take me below the green line, then what that tells me is that the difference between the sum, which is the green line here, and the partial sum, the red dot, must be less than the size of the next term. Okay? So the next thing that I'm about to add, I can see is going to take me too far. And so the error in my estimate with S5 is smaller than the size of the next thing I was about to add. And so here we see that A6 was negative 1/6. And so I decreased from the original partial sum S5 by 1/6. That means that S5 must have been closer to the answer than 1/6. Okay, so let's write that down. Our last hypothesis, and that is that the difference between the true sum and the partial sum is going to be less than the next term that I was about to add, which would be absolute value of an plus 1, or equivalently bn plus 1. Okay? All right, so those are our observations based on these examples, and it turns out that all of those observations can be true. Or not can be, they are true. For any alternating series, these things are going to actually be hold, and so they're going to hold. And so rather than just claiming their hypotheses, I will refer you to the book for the proof, but there's actually a theorem that defines the alternating series test. That says the following, that if the terms in an alternating series get smaller, well, it's convergent, at least conditionally. It may converge absolutely too, but at the very least it converges conditionally. Secondly, we can conclude that the partial sums are always going to either be a little bigger or a little smaller than the true value. And so if you take two consecutive partial sums, the true sum is somewhere in between. And then lastly, that if you want to use a partial sum as an estimate, you can be confident that you're going to be within the next term of the true value. Okay? So those three properties make up what we'll call the alternating series test, and we can apply those. And in the next video, we'll do that to a couple of examples to see how we can actually get pretty good estimates for exactly what alternating series converge to.